Swayam Prabha. Digital India. Educated India.
Good morning, students. So, as discussed, today we will start with graph algorithms. So, we will specifically do graph traversals to start with, and as we get introduced to more and more different techniques of algorithms, we will see other graph related methods. Okay, but to start with, we will look into graph traversals. So there are two major kinds of graph traversals that we will look into. DFS, or the depth first search algorithm, and BFS, or the breadth first search algorithm. So the idea would be as follows. We will start with DFS. We will then discuss the algorithm, start with an idea of what is DFS, algo for DFS, complexity analysis, applications of DFS. We will talk about two applications: cycle detection and topological sorting. And finally, DFS plus an application. So this would be the pipeline of things. So we will start with the idea of what is DFS. Depth first search, or DFS, is a systematic method of visiting the vertices of a graph. Its general step requires that if we are currently visiting vertex U, then we next visit a vertex adjacent to U, which has not been visited so far. Note that there are quite a few keywords. Okay. First, it's a systematic method of visiting vertices of a graph. Okay. The step requires that if we are currently visiting a vertex U, then we next visit a vertex adjacent to U, which has not been visited so far. So I remind you that adjacent means a neighbor of U in the graph. Just to recap. Okay. Now, if no such vertex exists, then we return to the vertex visited just before, and the search is repeated until every vertex in the graph has been visited. Again, note there are a few important things. So, if there is no further such vertex which are neighbors of U and has still not been visited, then we go back to the vertex that was visited just before and do a search, okay, until every vertex in the graph has been visited. So this part, actually, if you look at it carefully, it tells you that we are doing some sort of a recursive call here. Okay, so basically, if you do not find the neighbors of a particular node uh, that are not already visited, then you go back to the ancestor of that node and you look at the neighbors that have so far not been visited of those ancestors. If all the nodes that are neighbors of the ancestor are also visited, then you go to the ancestor's ancestor and you keep on doing this. So there is a recursion embedded in this strategy. Okay, so we will look at it into more details now. So DFS, why depth first? So DFS actually uses, as we have already seen from the previous slide, that DFS uses a strategy that searches deeper and deeper. Into the network. Okay, so again, deeper and deeper. So this is where it derives its name from, depth first. Okay, so goes along a depth unless all the vertices along that depth have been visited. Have been already visited. So in the pseudocode that we will write just now, there are certain things that we will use, certain notations that we will use. Okay. So initially, all nodes, okay, are initialized to color white. Okay. So this white color node also indicates that the node is undiscovered. The node is undiscovered so far. Okay. And we will also set the parents of each vertex to null. These are the two initialization steps. Okay. So now our procedure will begin. We will begin by selecting a node, say U, from the graph. Okay. And set its color to gray. Okay. To indicate that the node has now been discovered or visited. Okay. And we will assign to this node a discovery time zero. Okay. The discovery time associated with this node will be 0. Now, for each V, which is a neighbor of U, and is still marked white, we visit it recursively. So this means we go to V, and then from V we mark it gray, and then go to one of the neighbors of V, and we keep on doing it until and unless we have exhausted that path, and then we come back. Okay. So if no white descendant of V exists, then we mark V as black in color. Okay. So at this point, we assign a finishing time to the node V. Okay. So like the discovery time, we also assign a finishing time to the node V. Okay. And from here, we return to the ancestor of V, which we will term as pi of V for further exploration. So again, in a nutshell, you start from a particular node, you color it gray. Initially, all nodes are white. You start from a particular node U, color it gray. Now you look at one of its neighbor V. If it is white, you color it gray, and you keep on doing this recursively. And once a particular vertex has all its descendants marked as gray, that is, they are visited, you mark that particular node as black, that is, all its descendants have been visited. And now you go back to the ancestor of that node and you keep doing further exploration. So as you understand, there is a recursion involved in the whole process. Okay, and we will see how we implement this. Okay, it's a very simple algorithm. We will see how we implement this. Using a small pseudocode. Algorithm DFS of a graph G. Input graph now you can feed the input either as an adjacency matrix or an adjacency list. Output the depth first tree or forest, whatever the case may be, of the graph G. DFS G. For each vertex for each vertex U in V, do color of U is set to white, ancestor of U is set to null, and out of for loop time is set to 0. Now for each vertex U in V, do if color of U is white, then call the function dfs visit u. Okay. Now dfs visit is a recursive function which is written as follows. Color u is set to, as we said, is set to gray. That is, u is discovered. Du is set to time. So du is the discovery time. D is the discovery time. Time is incremented. Now, for each v, which is a neighbor of u represented by adju, do if color of v is white, then make u the ancestor of v and call dfs visit v recursively. So this is where you are exploring the edge uv. Once this is over, color of u, that is, at this time you are sure that all the neighbors of u have become non-white. Okay, color of u becomes black. So this means exploration of u done. And if u is set to time and time is again incremented. So this fu here is the finish time. So now you see, after the complete exploration of the graph, all nodes will become black in color and will have a discovery time as well as a finish time. Okay, and the DFS traversal will be stored in the IV structure, right? This could be an array, this could be a structure depending on your implementation. Okay. So the complexity is very simple. Okay, this part takes order n, where, so let us say mod v is n and mod e is m, and DFS visit has to explore every edge. Okay. Since it has to explore every edge, so therefore this will be order m. Okay. So the initialization is order n. So this is the initialization part. This is order n, and the DFS visit, since it has to explore all the edges, okay, through this adjacency list traversal. Okay, so this exploration can take order m time, and therefore the order of the whole algorithm is m plus n. So a DFS algorithm takes order m plus n time. So this is order m, as we said, and the initialization is order n. Okay. So we will trace this using an example so that it becomes clear to you. So after the traversal, actually what we'll end up to is a depth first tree. Okay, and this maps exactly as the DFS visit calls. Okay, since your u is equal to pi v if and only if DFS visit was called during a search of use adjacency list or matrix, whatever representation you are using. Okay, so now we will trace an example to exactly see how the algorithm works. So I will show you some of these steps, and then as a homework you will do the rest of the steps. I'll show you the initial steps and the final result. As a homework you should do the rest of the steps. So let us say we have a graph like this. So let us assume that this is our graph. To start with, so this is a directed graph. with directed edges, okay, and we start, say, our exploration or our traversal from U. So traversal starts from U. Okay. So since I do not have um, a gray color, I will use a blue color to represent the gray color. So please bear with me. So the blue color will actually represent the gray color. It's all the same. So we, as I said, we start with U, and now inside the edges, I will write the start and the finish times. First, let us draw the graph again. So as you start your exploration, U becomes gray in color, okay, and the discovery time is set to 1, and we still don't know, the exploration is on, we still don't know when it will reach the finish time. Okay, in the next step, what we will do, we will take one of the edges, okay, from U. Let's say we take the edge U to V. So we explore U to V. We could have also explored U to Y. So this tells you why the DFS tree that we will get finally might be not necessarily the same. Depending on the path of exploration that we are taking, we might get different variants of the DFS tree. So one of the trees that we will land up to is what we are drawing here. So let's say we take up the edge UV. Then in the next step, we have so now the node V has been marked gray. Okay, and its discovery time is set to 2. We don't know the finish time. Okay, now in the next step, let's say from 2 we have only one edge to explore, that is VW. Okay, from V we have only one edge to explore, that is VW. So we will explore that and go to the next state of the graph. Now you see U is explored, V is explored, and also W is explored. And we also have the discovery times for them. Okay. So after this, what should be the next step? From W, there is no edge which can be further explored, right? From W, there is no edge that can be further explored. So now, as per the algorithm, we will come back to its ancestor, which is 2 in this case. Sorry, which is V in this case. So from W, since there is nothing to explore further, we will come back to V. Now you see in this stage, in this particular stage, since there is no further white nodes that can be explored from W, so W becomes black. Okay, and now along with the start time of W, we can also assign the finish time of W. Okay, and we come back to V. Now again, from V, we have no other edges to explore. Okay, when we are at V, we have no further edges to explore. So therefore, in the next step, the state of the graph will be as follows. Now 2 has also become, sorry, V has also become black. Along with W, P has also become black because there is no other white node left to be explored from V anymore. And we now also have the finish time of V. Okay, so in this way the exploration continues. Now after this, from this step you will go to 1, and from 1 you will have another vertex, another white vertex that is left to be explored. You will explore this. Okay, and from there you could have gone to V, or you could have gone to X. You would take any one of the course. V, since it is explored, you will not take that path. You will take the unexplored path, and then you will finish here. And then after that you will, so since the set of nodes are still not exhausted, you will go to Q, and then from Q you will explore Z, and your exploration will stop there, because there is no other node in the whole network which has not been visited. So the final snapshot would look as follows. So at this point, in the final snapshot, everything will be black. So in this way, we will complete the exploration of the whole graph. So your final DFS tree would look like, if you now look at your pi, okay, then you will easily get the final DFS tree. U, V, W, Y, X, Q. This is why we said that you might also land up into a forest. This is an example where we land up into a forest actually. So there are two trees. one here and one here. Okay. So once we have got our hands dirty with the idea of DFS, we can now discuss another important aspect called edge classification. So there are basically 4 types of edges. The first one is called a tree edge. Okay. So this is edge UV is a tree edge if V was first discovered by exploring the edge UV. So remember the word first discovered. Okay. If V was first discovered by exploring edge UV. Okay. So the tree edge therefore establishes a direct relation between a node and its ancestors. Sorry, node and its direct descendants. Okay. In other words, the discovery time of U is strictly less than the discovery time of V. Okay. Sometimes we call this a low to high nodes connection. Okay. Or a low to high node relation. So this is a direct so it's a relation between a node and its direct descendants. Okay. This is what we need to remember. Next comes back edge. Those non-tree edges UV that connect a vertex U to an ancestor of U. So a back edge actually establishes a descendant to an ancestor relationship. Okay. Sometimes this is termed as high to low nodes. The next in line is a forward edge. Non-tree edges connecting a vertex U to a descendant V. Again, they establish an ancestor to descendant relationship. Okay. So these again are low to high nodes. However, these are non-tree, okay, non-tree low to high nodes. So the tree edges are direct descendants. These are non-tree edges, okay. We will soon see an example and things will be more clear. The last one is a cross edge. All other edges that cannot be classified into any one of the above classes. Okay, so there is no ancestor descendant relationship. They are again high to low nodes. Okay, so let us take an example and understand the different types of edges. Let us say we have a small graph like this. So here, if this is a graph, see, I have intentionally colored it in different way. So some edges are colored green. So these green edges are, you immediately understand, these are tree edges. Okay. So involving direct descendants and first exploration. Okay. Now, the blue edge is what we call a forward edge. Okay. So you see, this is a non-tree edge, but it is also low to high. And it's a forward edge. The red edge is a back edge. Okay. It's again a non-tree edge and it has a high to low connection. Okay. And finally, the black colored edge is the cross edge. It has no ancestor descendant relationship. However, note that this is also a high to low and this is also a high to low. The tree edge and the forward edge distinction is easy because one is a direct descendant, okay, and reached through first exploration, while the other is not. However, the difference between back edge and cross edge is not so apparent. So the question is then how to distinguish between a back edge and a cross edge. Okay, it's not so difficult. You proceed as follows. Okay, so both of them are, as you understand, non-tree edges. Now starting, let us say, consider the non-tree edge UV. Okay. Now starting from U, okay, traverse the depth first tree to visit U's ancestors. If V is found in the ancestry list somewhere, then UV is a back edge. Else, if we reach the root of the tree without finding V as an ancestor, then UV is a cross edge. Okay, so if you have explored the full ancestry list and still you have not found V, then UV is a cross edge. Otherwise, UV is a back edge. So in the next class, we'll stop here. In the next class, we will discuss the different applications of DFS, followed by introduction to BFS and one of its applications. Thank you.